regular Moose. He's cute. What did we do to Moose when Moose looks like this? We narrowed him. What are the two things we did to make him narrower? Horizontally, we shrink him, squished him, and vertically, we stretch. If I make Moose look like this, what does he look like?
Wider.
What did I do to Moose to make him wider? Horizontally or vertically. So horizontal stretch and vertical shrink. That's what we're going to do all the time to our parabolas. Do y'all know who these people are? This is J-Lo. Okay, who's this? Who is this?
I forgot her name.
This is Hannah Montana's aunt, also known as Dolly Parton. Okay, if you look at these two ladies, besides the fact that they're old and don't talk about their race, how are they different from each other? She straight up said it. Okay, let's say it in a nicer way. Abby, can you say again, but in a nicer way, what you just said?
One bigger breast.
Okay.
Other one a bigger body.
She's really just going to say it. All right. One of them is bigger on top, and one of them is bigger on bottom. Do you agree?
Sure.
Okay. I mean, she's not wrong. That's what I was getting at, but you can say it nicer. So would you also say that this fraction is bigger on top or bigger on bottom?
Bigger on bottom.
That's called a J-Lo fraction.
The J-Lo fraction.
This is J-Lo. All right. J-Lo fraction. She's bigger on bottom. What would you call this fraction?
Bigger on top.
So this is a Dolly Parton fraction. We're going to be using types of fractions today to talk about the different kind of stretches and shrinks. We're going to hold on to the signs today. Okay, to talk about the types of stretches and shrinks we're doing, it has to do with the number that we're going to multiply by these functions. They're either going to be Dolly Parton numbers or J-Lo numbers. Oop, if I just wrote down the number 3, is that a Dolly Parton or a J-Lo number?
It's like
It's 3 over 1, which makes it a Dolly Parton fraction. Now what about this one?
J-Lo.
Bigger on bottom. Even though it's barely bigger on bottom, it's bigger on bottom. I'm going to be referring to these fractions as J-Lo and Dolly fractions. Okay, do not go home and tell your parents that you learned about J-Lo and Dolly in math class today. Okay, what happens in math class stays in math class. Cool?
That's cool.
Okay. On to our transformations. Now, we're going to do what's called dilations of our parent function. You did this last year with shapes. You made them bigger and smaller. We're going to do the same thing. This is what we did to Moose a little bit ago. We stretched him out or we shrunk him down. We're going to be changing the shape and the size of our parent parabola. By the way, what was the quadratic parent function?
Fx equals x squared.
Perfect. F of x equal to x squared. 4 types of stretches and shrink, and they're in 2 categories. We're going to talk about the first 2 to begin with. There are verticals. Okay? Now, they both get differences between J-Lo and Dolly numbers. When we multiply something in the very front, we're going to be doing the vertical stretches and shrinks. With your highlighter right now, will you highlight the quotation marks here just on the vertical side? The quotation marks in the top box say vertical stretch by a factor of 3. In the bottom box, they say vertical shrink by a factor of 1/3. Where on the top box did they get the number 3?
In front of the x.
In front of the x. In front, is it inside parentheses?
No.
No, it makes it a vertical transformation. And that number 3 is a Dolly Parton number. This Dolly Parton number is going to make the graph narrower. Do y'all see how your parent function's there and then inside it almost is a smaller, skinnier function? Yeah. It's a narrower function. So what we've done is we've taken the Dolly number of 3, multiplied it by my parenthesis in the very front, and we've made our graph narrower.
Yeah.
That is called a vertical stretch. With your arms right now, I need you to be a parent parabola. And if I told you to stretch, your arms would go up and they would get narrower. That's called a vertical stretch. So go back to be the parent function. Stretch your arms up. Stretch, 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 stretch. And they got narrower. They got closer to your ears. So that is a vertical stretch. Now, in the bottom one, it says vertical shrink by a factor of 1/3. Where did I get the 1/3 from?
In front of the x.
And in front of the x, when it's a J-Lo number, When it's a fraction, it's actually going to make my graph
Bigger.
wider. So what I would do is, if I was the parent function, when I shrink, I'm getting smaller. I'm getting wider. Shrinking towards the x-axis. So J-low is always going to be the vertical shrinks.
Bigger.
Okay, it's going to make it wider. Cool?
Cool.
Okay, we're going to go to the inside and talk about the vertical ones first. So flip your graph open. We're going to talk about these two before we go to the horizontals. The first vocabulary word here is a vertical stretch. If you do not yet have your parent function typed into Desmos and made dashed, will you please do that for me? And then I also want you to type in this function that I'm highlighting in black. It has a 2 multiplied in front of the f of x. Is that 2 a Dolly Parton or a J-Lo number?
Dollar.
It's a Dolly Parton. So what is a Dolly Parton number going to do?
Shrink. No.
It's going to stretch it. What does the stretch look like when I type that into Desmos?
You're right, Mickey.
When I type it in, did it make my parent function wider or narrower?
Narrower.
Narrower. So we're going to say that it got narrower, and we're going to do a sketch. I'm not going to be super accurate today on these stretches and shrinks. I just need to make sure you know that it's going to be inside or narrower than the parent function. You don't have to be super accurate unless you want to make a table and go for it, but it's just a narrower graph. The way that we're going to answer these questions, like to write it down on a quiz or on your homework, would be to say if we see it's narrower or we see that there's a 2 multiplied in the front, because that's going to be our indicator of a vertical stretch, you would say that this is a vertical stretch by a factor of 2. How did I get the 2 part of this answer?
Because the 2 in front of the x.
The 2 in front of the f of x, okay? The 2 in front of the x squared. It's going to show me what the factor is that I'm going to use here. That's how you would answer this question if I showed you this graph or the equation and asked you what transformation is this. You would say, oh, it's a vertical stretch by a factor of 2 because there's a Dolly Parton number in front of it. Okay, but don't trust me. If you have yet to get this graph into Desmos, please do so. It does get narrower. Agreed?
Yes.
Cool. We go to the next one. It's called a vertical shrink. What kind of number is in front of my equation this time?
J-Lo.
1/2, which is a J-Lo fraction. The J-Lo fraction, is it going to make this graph wider or narrower? Wider. So let's graph one that's wider, and then we'll double check using Desmos to make sure that it actually did make that wider. So check it in there. Make sure that putting a 1/2 in front of the function is actually going to make it wider. Don't take my word for it.
Oh my gosh, our favorite calculator.
You're right. My favorite calculator. The way that we answer this question, if I asked you what was going on here, showing you either the equation or the graph, would be to say that this is a vertical shrink by a factor of 1/2, using that J-Lo number. It would make my graph wider visually, so I know that that is a vertical shrink. When you've got all this written down, go ahead and close your notes so I know you're ready to move on. So I know when I can go back to the front, because we're going to go back to the front and talk about the horizontal versions of stretch and shrink. Back on the front side, we're going to talk about our horizontal stretches and shrinks. Now, we asked you this at the door. Since these are going to be horizontal, what should you probably immediately start thinking? HIO. What does HIO stand for?
Horizontal, inside, opposite.
Horizontal transformations are inside parentheses and they go the opposite direction. So do you see that now when I have these numbers in here, they're on the inside of the parentheses instead of out in front of it? That's your indicator that this is a horizontal transformation and that it's going to be a horizontal stretch and shrink. Now, I told you this is the opposite. So immediately when you see it's on the inside, I want you to take that number and I want you to flip it over. If I take 1/3 and I use the opposite, what's the opposite? The reciprocal of 1/3. 3 over 1, right? Is that a J-Lo or dolly?
Dolly.
That's a dolly number. Dolly numbers are always my stretches. Dolly numbers are always my stretches. But since this is horizontal, it's going to be the opposite looking graph. This is no longer going to look narrower for a stretch. It's actually going to look wider. But dolly numbers give me a stretch. It's just all the opposites because horizontal is inside the parentheses, is the opposite of everything. Okay, if you look at the one at the bottom, let's highlight how you say it on this front. This is called a horizontal stretch by a factor of 3. That's how you would say it because that's the dolly number I'm using. On the bottom, we know that this is going to be a horizontal shrink by a factor of 1/3, but where did I get that 1/3 from?
And the 3 got flipped.
Yeah, 3 was inside, which means I'm immediately going to use the opposite. What's the opposite, or the reciprocal of 3?
1/3.
1/3. That is a J-Lo number. J-Lo numbers are always my shrinks. J-Lo numbers are always my shrinks, but since it's horizontal, it visually looks different. This time it's not going to be wider, it's actually going to be narrower. Horizontal are inside parentheses, the opposite fraction are the opposite visual. I forgot what word I was supposed to say out loud. When you've got this, flip it open so I know you're ready to see the other 2 examples. These are the last 2 words we're learning of all of our vocabulary for transformations. If we look at the horizontal stretch, we see that number is on the inside, so we immediately think, I need to do the opposite. So what kind of number am I actually using in here?
A dolly.
A dolly, because it's 2 over 1. That's a dolly number. Dolly numbers are always my stretches. But since this is horizontal, is it going to get narrower?
No.
No, it's going to get
Wider.
But don't take my word for it. You have a way to 100% check your work every time. You should no longer ever have to ask me what this is once we learn these 10 words, because visually, this is what it does. Check it in Desmos against your parent function. Type in g of x equal f of 1/2 x and see it get wider. See it get wider. Now, the way that we would say this answer, just to make sure we have that written down, is that this is a vertical, it's not vertical, it's horizontal. It's a horizontal stretch by a factor of 2 over 1 or 2. Because I used the opposite number, I used the dolly number instead of the one that we saw originally. Horizontal, always the opposites. Objectively, this is a little confusing, so if you're like, what? Objectively, this is confusing. Did it get wider when you typed this into Desmos? Cool. When you typed in 1/2 on the inside, it got wider. Because it's actually a dolly number we're using when you flip it over. I see some of you getting ahead of me, so I'll catch up to you. On the bottom one, we've got a number on the inside, that's 2. But since it's on the inside, when I'm actually looking at it, what number should this be? 1 over 2, which makes this a J-Lo number. J-Lo numbers are always my shrinks. But since it's horizontal, it should be the opposite of the other shrink. It's going to get narrower. But again, don't take my word for it. Check it in your Desmos. Make sure it actually does get narrower than the parent function.
It does.
The way that we would answer this question if we were writing down what it was is that this is an horizontal shrink by a factor of 1 over 2. Very good. So again, I'm using the flipped number, the opposite number, that's the reciprocal, in the words or the verbiage of my answer. Okay, horizontal is weird. Horizontal is inside and its opposites. Horizontal is inside and its opposite. But J-Lo's always make it shrink and dollies always make it stretch. It just depends on the direction as to what the shape actually looks like. Okay? If you look for a second, I'm going to zoom out. We have 4 types of dilations. We have vertical stretch, vertical shrink, horizontal stretch, horizontal shrink. What do you notice about like the ones on this diagonal right here? Did y'all notice anything about this?
They shrink.
A vertical stretch, doesn't it kind of look like a horizontal shrink?
Yeah.
They both get narrower.
Yeah.
Okay, and what about these? What do you notice?
They look the same.
They look the same visually. They're different. The only way we can tell them apart when we're looking at them is by the equation. If the number is on the inside, we're dealing with the horizontal ones. If the number is multiplied on the outside, we're dealing with the vertical ones. Okay, remember these are the ones multiplied in front of it. So if I were to add or subtract a number on the inside, I'm back to doing my shifts from last class, not the stretches and shrinks.